In this tutorial, we will present the main spread spectrum technologies, and then we will talk about the multiplexing and multiple access techniques. But finally, we will discuss how the performance could be changed within the same technology by tuning its parameters. Let's start with the spread spectrum techniques. Spread spectrum techniques are ways of distributing a signal over a wider bandwidth, thereby enabling the advantages of wider bandwidth transmission to be achieved. The spread spectrum techniques that we will talk about it in this lecture are not in themselves modulation techniques, rather they are ways of spreading the spectrum of a carrier that is modulated by one of the techniques that we have already discussed in the previous tutorials, or by other modulation techniques. Rather, they are ways of spreading the spectrum of a carrier that is modulated by one of the techniques we have already discussed. The two major modulation schemes, spread spectrum modulation schemes that we will talk about it are frequency hopping spread spectrum and direct sequence spread spectrum. So frequency hopped spread spectrum, as its name implies, frequency hopped spread spectrum works by changing the carrier frequency of the modulated signal, hopping from one frequency to another. It may be classified as either slow frequency hopping or fast frequency hopping, according to whether the rate of frequency hopping is greater or less than the data rate. Slow frequency hopping. With slow frequency hopping, the signal modulates a carrier using one of the modulation schemes that we have discussed previously, as for example OOK, on-off keying. So the signal modulates a carrier at one frequency for several symbols, then the carrier wave frequency changes, and for the next few symbols the signal modulates the new carrier. In other words, it's just the symbols of the signal modulates the new carrier. We call using some ordinary modulation, but it will be changed after a specific number of symbols. For example, in mobile communications, multipath fading means that at particular frequencies the effective channel attenuations becomes very large. The frequencies at which this happens depend upon the particular path between the terminal and the base station, and are affected by the presence of buildings and other obstructions of the route. When the mobile terminal is moving, the frequencies at which the fading happens keep changing, so it can't be predicted and avoided completely. By frequency hopping, the system ensures that the communication link is not trying to use the bad frequency all the time. Hopefully, the communication only hits a bad frequency occasionally. When it does hit a bad frequency, it might lose a burst of bits, but these can be corrected by error correction channel coding. Another advantage to frequency hopping, particularly relevant to military application, is that frequency hopping signals are difficult to disrupt or to jam. This is true of spread spectrum signals in general. The reason for this is that a conventional narrowband signal can be jammed by swapping the signal with a high power signal at the same frequency. To achieve the same effect on a frequency hop signal, the jamming signal has either to jam over the whole bandwidth used by the hopping sequence or else to follow the hopping sequence in synchronization. Furthermore, a third advantage to frequency hopping also of interest for military applications is that it offers some resistance to eavesdropping, because to follow the signal you have to know the hopping sequence, which may not be possible for someone determined to listen it, but helps prevent casual eavesdropping. Let's continue with the second type of frequency hopping, which is fast frequency hopping. In fast frequency hopping, the carrier frequency changes at a rate faster than the data rate. As a consequence, the data bits are broken into smaller units referred to as chips, as illustrated in the following figure. There are different ways of describing what is happening here. For some purposes, it's useful to think of the whole hopping pattern during a data bit as a single symbol. One symbol is then made up of 7 chips in this case. This is a viewpoint that we should be adopted most of the time. For other purposes, however, it's useful to think of the chips as whole symbols, and the symbol generated is preceded by a line code in which each bit is encoded to a block of 7 consecutive states. In the latter case, the signaling rate is equal to the chipping rate, while in the former case, the signal rate is equal to the data rate. As with slow frequency hopping, the hopping sequence is predetermined and known by both the transmitter and the receiver. Once again, signal detection can be done by the receiver correlating against the hopping pattern. The advantages of slow frequency hopping, security from eavesdroppers, and tolerance to bad frequencies in the channel are also found with fast frequency hopping. Notice that for fast frequency hopping, bad frequencies now affect every data bit, but only so it affects only a small part of each bit. In slow frequency hopping, bad frequencies affect whole data bits, but only some of them. Let's start with direct sequence spread spectrum, DSSS. The idea of shipping and the use of a sequence of chips to represent 1 and another sequence of chips to represent 0 raise the possibility of another way of creating a wide bandwidth signal, but which does not use frequency hopping. To see how this might work, let us look at a signal voltage pulse shown below. I remind you that a pulse, like the one presented in the following figure, is analyzed into a set of sine waves of various frequencies. In case we have a pulse like this, where we have a sudden transition, whether in frequency, amplitude, or phase, so normally when we have such sudden transition, it's apt to generate signals with a wide frequency spectrum. So the sharp corners of the pulse shown in this figure indicate that we can expect the spectrum to have high frequencies. The other figure shows how the energy of a pulse like that would be distributed across a spread of frequencies. Shortly, the duration of the pulse puts relatively more energy into the higher frequencies. When it comes to sequences of pulses, rather than isolated single pulses, the way the energy is distributed is affected by the duration and separation of the pulses, but the same general principle of a spread of energy over a wide frequency spectrum holds. However, by choosing certain patterns of pulses, the way the energy is spread across the frequencies can be tailored to some extent. This is the essence of direct sequence spread spectrum, where patterns of pulses are used that give an energy distribution resembling that of noise. The following figures give an example of a set of pulses or chips, as they would usually be called, that has a noise-like spectrum. A sequence of chips with the required property of having a noise-like spectrum is called the pseudo-noise sequence, or PN sequence. It's sometimes also called a pseudo-random sequence. The sequence is defined by the sequence of ones and minus ones. Hence, the sequence in the following figure can be represented as 1 minus 1, 1 minus 1, minus 1, 1, etc. This set of numbers is called a code, or a spreading code, because it spreads the spectrum of the original data. Many suitable codes can be devised. Practical spreading codes often have many more digits than I have just used in this example. The idea with the SSS is to use a sequence of chips such as that to represent a 1 in the data to be transmitted. Every 1 in the data would be represented by the same code. Every 0 would be represented by another code, usually the inverse of the code used to represent 1. All the 1 chips would become minus 1, vice versa. How the chips are transmitted depends on the modulation methods used. For instance, if XK were used, all the ones in the code would be represented by one carrier frequencies and all minus ones by a different carrier frequency. Because the sequence spreads the spectrum of the spaceband signal, it also spreads the spectrum of the modulated signal. Reception of the data depends on the receiver knowing the codes that are in use by the transmitter and being able to synchronize with the transmitter. I will not explain how synchronization is achieved, but if these conditions are met, the original data can be recovered. For receivers that do not know the codes, the transmission just looks like noise, and if the transmission power is not too great, the existence of the transmission can pass undetected. For these reasons, DSS has found its first uses in military communications. However, the technique is widely used in non-military applications, and the development known as complementary code keying is used in 802.11b Wi-Fi standard. Multiplexing and multiple access. Let's start by the spectrum sharing. Two wireless techniques that have become very common with the rise of digital telecommunication are orthogonal frequency division multiplexing (OFDM) and code division multiple access (CDMA). The first of these, OFDM, is widely used in digital broadcasting. For instance, in digital audio broadcasting, DIB radio, and a more recent radio system called Digital Radio Mondiale (DRM), to give just two examples. CDMA is an example of multiple access and is widely used in some mobile telephony techniques. Multiple access is the sharing of a communication channel among many users. But so is multiplexing. What distinguishes multiple access from multiplexing is that In multiplexing, the allocation of the resource is controlled by the resource being shared. For instance, time slots are predefined for time division multiplexing, or frequency are laid down in frequency division multiplexing. Multiple access, however, is more of a demand-led process. The separated user claims a share of the resource rather than taking a share that is offered. The following explanation provides us more information about the difference between multiplexing and CDMA as a multiplexing technique. Channels that are divided neither in frequency nor in time can nevertheless be multiplexed in such a way that they can be separated afterwards or demultiplexed. The key to this is the use of codes, very much like those described in connection with the SSS. Each user is given a unique code unique within a service area. Multiplexing is achieved through the simultaneous use of many different codes. As we have so in connection with the SSS, the code defines a set of pulses or shifts that can be used to represent ones in the data. With suitable modification, a version of the same code can also represent zeros. Often the modification is simply an inversion of code. Although other transmissions appear to be noise as far as any single transmission is concerned, this does not mean that they have no influence on the reception of particular signals. The more users there are, the worse the signal to noise ratio becomes, and this is always likely to be deleterious, as we saw in connection with channel equation. So in channel equation, we have seen that the channel capacity is related to the channel bandwidth and with logarithmic relation with the signal to noise ratio. However, the process is a gradual one, and additional transmissions lead to a gradual deterioration of the service each user receives. With other multiplexing methods or techniques, there is usually a fixed limit to the number of users who can be multiplexed together. Multiplexing can be illustrated as a single point-to-point link, which behaves as though it were several links in parallel. At each end there is a multiplexer which shares the single link between the multiple incoming and outgoing channels. Let's start now with the orthogonal frequency division multiplexing, or FDM. Frequency division multiplexing is usually described as a way of allowing several communication channels to coexist with a particular section of frequency spectrum using different carrier frequencies. It allows the waveband to be shared among many users. by giving each user a slice of the waveband. Orthogonal frequency division multiplexing similarly use many carriers, although in OFDM they are called subcarriers. Each subcarrier is associated with its own stream of data. However, whereas in radio wave bands the carriers are typically separated by several kilohertz or more, in OFDM the subcarriers are typically only a few tens of hertz apart. Also, whereas in conventional frequency division multiplexing, each modulated carrier has data from a separate source. In OFDM, the modulated subcarriers usually carry data from a single source. So, in OFDM, the modulated subcarriers usually carry data from a single source and not from multiple sources as the traditional frequency division multiplexings do. Naturally, some ways of distributing the data from a single source across the many subcarriers needs to be found. Of the modulation methods already described could in principle be used. The following figure shows one way for doing this. Start at the top left with the serial data stream 10111110, which is to be transmitted. This data stream passes to a serial to parallel converter, which converts it to 8 parallel streams of data. The top stream emerging from serial to parallel converter carries the most significant bit. In this case 1, the bottom stream carried the least significant bit, 0 in this case. In between are streams for all the other bits of the now parallel data stream. All 8 bits emerge simultaneously from the serial to parallel converter and are to be transmitted simultaneously. I have not said anything about how the individual subcarriers of them are modulated. Any of the modulation methods already described in this part of this block could in principle be used. The system of the following figure used quadrature phase shift keying. You may recall that QPSK used 4 symbols and so allows 2 bits per symbol period to be transmitted. This is why in the following figure the top 2 output lines from the serial to parallel converter passes into the same QPSK modulator. This modulator is shown as operating at frequency 0. The following figure shows that the other subcarrier frequencies in use are F1, F2, and F3, each modulated using QPSK. The outputs from all the modulators are transmitted simultaneously. At the receiver, the entire process is reversed as seen on the right side of this figure. It's not immediately obvious that in OFDM what constitutes a symbol. Let's take the system of the following figure. Each subcarrier carries a 2-bit number and so has 4 signaling states. By taking the system as a whole, how many symbols are there? To answer this question, It is important to remember that with OFDM, the receiver receives all the subcarriers together. This is different from the position with, say, radio broadcast on the medium wave band, where the receiver is tuned to a single carrier. With OFDM, the ensemble of subcarriers is effectively one signal. Each state of this signal is a symbol. For example, let us designate the subcarriers of the following figure as A, B, C, D. Each of the subcarriers can take one of four possible states, representing 0, 0, 0, 1, 1, 0, 1, 1. Thus, the four possible states of subcarrier A can be represented as A1, A2, A3, and A4. Similarly, the four possible states of subcarrier B2 can be represented by B1, B2, B3, and B4. And same for the two remaining subcarriers, C and D. In any signaling interval, what is transmitted is a combination of A, B, C, and D, with each subcarrier taking one of its four possible states. For example, the following combination might be transmitted in a signaling interval: A1, B3, C2, D4. In another interval, one could have A4, B2, C3, D1 might be transmitted. Each unique combination of subcarrier signaling state is a symbol. In this example, there are four subcarriers, each of which one of the four states. So the number of symbols available is 4 over 4 equal to 56 symbols. If there had been only two subcarriers, but each capable of taking one of four states, the number of symbols would have been 4 power 2 equal 16. One of the benefits of OFDM is that it allows a high data rate to be achieved by increasing the bandwidth. Some applications of OFDM, however, do not use a particularly wide bandwidth, yet achieve quite a high data rate. Perhaps a better way to characterize OFDM is to say that it can be used to improve spectral efficiency. This will be illustrated by looking at a practical application in digital broadcasting. OFDM is used in a number of radio and television broadcasting technologies. For example, it's used in digital terrestrial television in the UK and Europe, and in digital audio broadcasting, the AB radio. However, it's by no means limited to radio and television broadcasting. The particular broadcasting context I want to use is digital radio. DRM was originally intended for use on the long, medium, and short wave bands as a replacement for conventional analog modulation. A development of a DRM Plus, has been devised for use on the VHF band. The DRM system is designed to work within the constraints that have traditionally been applied to broadcasters on the long, medium, and short wave bands. In Europe, that means, among other things, working within a band of 9 kHz, 10 kHz in the USA. The following figure shows the frequency spectrum of the broadcast signal using DRM. The following figure is 0 frequency. The center of the horizontal axis represents the carrier frequency. Conventional amplitude modulation is used. In this case, the 0 frequency is 9470 kHz. Or 9.47 megahertz. Which is in the shortwave band. As you can see, the raised part of the spectrum, which is the signal spectrum of the broadcast, occupies about 4.5 kilohertz on either side of this frequency, given an overall bandwidth of 9 kilohertz. The vertical lines in the following figure represent the individual subcarriers, which are so closely spaced as to run together in the graph. The modulation methods used on the subcarriers is not relevant to the following discussion, but for the record, it can be 16 QAM or 64 QAM. The DRM specification allows for different modes of operation, depending, for example, on whether the broadcaster is broadcasting to nearby receivers or over a long distance, and depending on whether robustness of reception or high audio quality is more important. In this mode used in the following figure, there are 182 subcarriers. The close spacing of the subcarriers makes us wonder about the sidebands. Since each subcarrier is amplitude modulated, it will have an upper and lower sidebands, which could encroach on adjacent subcarriers. One of the clever things about OFDM is to make the subcarriers orthogonal to each other, so that sidebands that stray into adjacent subcarrier do not cause interference. Orthogonality is achieved by carefully setting the subcarrier spacing in relation to the simple period. If the relationship between these two quantities is correct, the subcarriers will be orthogonal, and the intrusion of a sideband from one subcarrier into the frequency space allocated for a neighboring subcarrier will not be a problem. For the transmission in the following figure, the data rate is approximately 20 kilobits per second, which might seem on the low side for a system that is intended to give a reasonable or high audio quality. However, the digitized audio signal is subjected to lossy compression before modulation. The signaling rate per subcarrier of the OFDM system is quite low. This is one of the advantages of OFDM for broadcasting. The use of lots of subcarriers operating at low signaling rates helps to circumvent multipath interference, or at any rate to make it less noticeable. Some of the subcarriers might be momentarily lost at the receiver due to the multipath interference, but enough data will get through from other carriers to maintain intelligibility. Look to the part A of the following figure. In this part, it shows a hypothetical power density spectrum for a single carrier transmission. The range of shapes for the spectrum for single carrier transmissions is vast, so this is just one of many possibilities. In the second part, figure B, it shows the power density associated with an OFDM transmission, which has the same bandwidth as one in figure A. OFDM is also widely used in wireless data transmission. Notice that columns 5 and 6 specify numbers of bits per OFDM symbol. Symbol here is used in the sense described above, a unique combination of subcarrier signaling states. You should now be able to appreciate most of what the table 3 is showing. Just few points remain to be explained. First point is one you will doubtless have realized already, namely that at different data rates, different modulation methods are used. This is also a feature of other wireless standards where distance from the transmitter or noise degrades the quality of the received signal. The system drops down to a lower data rate and possibly a different modulation method. Look now at column 3 added coding rate. The data in this column relates to the convolutional coding used to encode the data. Convolutional coding adds extra bits to the data to enable errors to be corrected by the receivers. One way of thinking of coding is as replacing a string of data x bits long with longer strings y bits long. The coding rate tells you the ratio of x to y. Thus, for example, in row 1 of the table, the coding rate column tells us that every 1 bit of original data, there are 2 bits of data in the coded version that is actually transmitted. Column 5 gives the total number of coded bits per symbol. As mentioned above, in the context of OFDM, a symbol is a unique combination of subcarrier signaling states. The number of bits per symbol is the total of all the bits carried by the subcarriers. Column 5 refers to the number of bits per symbol that are actually transmitted. Because of the use of coding, this will be more than the number of bits that were in the original data. Column 6 gives the number of bits of original data that are encoded in each symbol. So, for example, in row 1, 6 megabit per second, every 48 bits of coded data convey 24 bits of original data. indicated in column 6. The number in column 6 and 5 are always in the same ratio as those in column 3. For example, taking the 54 megabit per second row table, column 6 and 4 are in the ratio 216 over 288, which cancels down to 3 over 4, as in column 3 of the same row. Note that one consequence of coding is that the data rate at which a device operates is not the rate at which a file of data is transmitted. For instance, if you have a 54 megabit file to transmit over a wireless link that is operating at 54 megabit per second, it does not follow that your file will be transmitted in 1 second. The coding means that the amount of data to be transmitted is significantly more than 54 megabit and will significantly longer than 1 second. The file active below is quite searching, but you have all the information you need to answer it. Explain. Are the same number of subcarriers used at every data rate? If yes, what is it? If no, how many subcarriers are used for each data rate?